Good afternoon. Before I start, I just want to let you know that the second assignment, you have the description online, but the subject matter for that, I will only finish it on next Tuesday. So you can start looking at the assignments, but you don't have yet all the information for starting. Okay? Today we're going to start looking at clustering algorithms, and I'm going to give a brief introduction to clustering, and this will be the main part of the unsupervised learning part of this course. So I'm going to talk about one particular clustering algorithm as an example to illustrate. Then on the next sessions I'm going to talk about more of them. So I'm going to talk about k-means and the variance, k-medoids. And then I'm going to use that algorithm to illustrate a fundamental approach in this in unsupervised learning, in many techniques in unsupervised learning, which is this expectation maximization technique. We're going to look at that a bit informally now. We're going to look at it more formally with probabilistic clustering with Gaussian mixture models. But today, just to give you an idea of this expectation maximization and to compare this clustering or unsupervised learning in general with the unsupervised learning approach we've been seeing so far. So let's start with the idea of clustering. What we want to do here is to group similar elements together. So this is still a very vague notion, but when you look at something like this, you can immediately see that there are three groups here. So we can do this intuitively, rather easily, grouping things together. Sometimes things get a bit messier, and especially if we are dealing with more than 2 or 3 dimensions, then it becomes hard for us to do this, but then we can use algorithms for that. So this is the basic idea. We want to group similar things together. So basically, we want to minimize the difference or distance or maximize the similarity within groups. So we can measure these in different ways, either by measuring similarity, so we maximize that within each cluster, within each group, or we measure some notion of dissimilarity, which can be a distance. A distance has a specific mathematical meaning, which must respect some axioms, like it must be positive, it must be symmetrical, it must meet the triangular inequality, and so forth. So some measures of dissimilarity can be distances, but we can be more general about that and just have some measure of how different the examples are. So if we measure in that way, we want to minimize those differences within each group and maximize the differences between the groups, and that's how we can select the group. We can look at it the other way and maximize the similarities within the group, so similar things go together, and minimize the similarities between groups. But this is the general notion of what we want to do with clustering. So we need to have some measure of these attributes or some way of comparing the different points and measure their similarities or differences. The motivation for clustering is most of the time to help us understand data. If we have to deal with a large number of examples, then it's hard to understand how they are related, but if we can group them in categories, it's much easier to sort things out in our minds. And this is what we do in general. So we have cats and dogs and mammals and fish and so on. We build categories of things and group them together to help us understand and deal with all the diversity. So meaningful grouping is an important thing for understanding anything. And remember that unsupervised learning, one of the main goals of unsupervised learning is to transform data into something that is easier to understand, something intelligible. Clustering also helps make sense of complex data by finding relations and finding what are the meaningful similarities to group things together, and this lets us identify meaningful groups. Sometimes groups that we didn't think of before, but we can see them in the data. We can also use clustering as a way of processing data to reduce the sample size, the number of points that we have. I'm going to show an example of that at the end, but basically we can represent our data set in a smaller data set that still captures the same structure. So let's see some examples. This is a classical and important example of a clustering algorithm, or the application, at least conceptually, of a clustering algorithm, which is Darwin's tree of life. So this is the famous I think, where he came up with the idea, and we have here an example of hierarchical clustering. We have a tree which spans or groups together all the descendants of some original species, and then we have branches that create subgroups of descendants of some of the descendants of the original one, and different branches of the large family tree. So this is a kind of clustering where we create clusters within larger clusters, and we build a hierarchy of clusters. A more recent example is this paper analyzing the distribution using data from ISPs and search engines in China that store the IP address or the cell tower where each person connects to the network, and these authors use the density-based clustering to identify neighborhoods in several cities where nobody existed. So there was no density there, and so basically they are ghost cities or ghost neighborhoods in these cities. So this is here we have an example of understanding some process and the organization of the data with hierarchical clustering. Here we see an example of a different type of clustering. There is no notion of hierarchy here, but we are looking at different densities to try to figure out in which regions there are fewer people living, or even almost nobody living. Another application could be to summarize data. So we can have prototypes that represent groups of data points, and they have also features like the data points, but they can be used to represent groups of similar points and thus reduce the sample that we are considering. This can help us improve performance in some cases where using many points could be harder. It can also help us compress data, segment images, and so forth. So here is an example. There are these clouds of points in blue here, but we can summarize this, reduce the data by representing them with these red crosses, with these prototypes, and we still keep the same shape, overall shape of the data. And we can control how much we reduce the data, so we can use more prototypes or fewer prototypes. Now, one problem that we have often is how we're going to define the clusters. For example, here in this data set, we could wonder if we have two clusters of points, the red triangles and the green triangles and the red circles, or maybe we have three clusters of points. So we represent this way. Maybe these four are a different cluster here because they are very close together and further apart from the rest. Or maybe we have four clusters or five clusters, and so we need to decide how many clusters in this case, or what are the criteria for determining the right number of clusters, and so on. So this is one basic problem in clustering, actually defining what clusters we want. Because in essence, in clustering, we are trying to project from a continuous space, which is the set of features that are generally continuous. Sometimes they're not, but most of the time they are. And we want to project that into a categorical space where we have a finite number of clusters and the points belong to clusters. We'll see next week that we can also do that in a continuous way with fuzzy clustering and probabilistic clustering, but basically we have this problem of how we're going to decide how to cluster our examples. And here, there are the two examples. Going back to those two examples I showed, we have this first decision. Do we want to partition our data into a set of clusters all at the same level? So this would be partitional clustering. Or if we want to create clusters within larger clustering, and this would be a hierarchical cluster. So here, just one short note on the word clustering. Clustering can either be used as a verb, which means to create those groups, or as a noun. The clustering is the set of clusters that we get in the result. So we have these kind of choices. In this case, we have a partitional clustering. We created 5 clusters from these points, and they are all at the same level. Or we can have hierarchical clustering. Here I'm representing with 2 different colors the 2 large clusters at one level, and then each of these large clusters has subclusters. So in this case, the red cluster has 3 subclusters here with 3 different symbols, and the green cluster has 2 subclusters. So this is an example of a hierarchical clustering. We can also, we need also to decide how we assign each data point to a cluster. So exclusive clustering means that the data points can only belong to one cluster. Overlapping clustering means we can attribute each one point to more than one cluster, so clusters can overlap in the set of points. Fuzzy clustering, the assignment of a point to a cluster is not just binary. The point does not just belong or does not belong to the cluster, but it has a continuous value between 0 and 1. So it can partially belong to a cluster or totally belong to that cluster. Probabilistic clustering is similar. We also have a continuous value for the assignment of a point to a cluster, but those values must represent probability. So the point must be assigned somewhere with a total probability of 1, meaning that these values must be distributed so as to add up to 1 between the different clusters the point belongs to. We can also, we must also decide on the coverage of the data set, the data points. If we have complete clustering, then all our points are assigned to some clusters. If we have partial clustering, we can leave some points outside and not assign them to any cluster. So another thing that influences how we do clustering is the data. So in some cases we have these well-separated clusters, meaning that the data itself is very well behaved and shows different groups that are very tight and they are far apart. So this makes it easier to determine how we're going to cluster our groups. When we decide how to cluster our groups, then we have different algorithms. So this is not something that you need to memorize all these differences, but this is basically a roadmap for the different algorithms that we're going to look at in the next session. So we'll start with this one, which is prototype-based clustering, where we choose some representatives in the space where our data exists to represent groups of points. And then we have some way of assigning each point to one of these representatives. For example, in this case, we use distance to the prototype, so all this region here belongs to this prototype because all of the points here are closer to this prototype. Then there's another region belonging to this one, and so on. We can define clusters in other ways. For example, by contiguity, we can determine that this is one cluster because there are many points close together here, and they form a contiguous shape. And then here we have another cluster because it's also a contiguous shape, but it's separated from the first one. Or density-based clustering, where we cluster high-density regions. They form one, each high-density region forms one group, but then we have these low-density regions where the points are not assigned to any cluster. So this would be an example of a density-based clustering that is a partial clustering. So we don't demand that all points be assigned to one group. So basically, we need to decide a lot of things when we're trying to do clustering. We need to decide on the similarity or difference measures by which we're going to determine which points are closer to each other. We need to determine on the relation between the examples and the clusters, if they, all of the examples are in cluster, if only some of them belong to clusters. When they belong to a cluster, if they must do so binary, or either they belong or they don't, or if they do so partially with a continuous value, if they can belong to more than one cluster, and so forth. So these decisions will depend a lot on what, on the way we're trying to understand the data and what would be meaningful for the data. Then we need to determine how we create these clusters. If we have prototypes that represent sets of points, if these prototypes must be part of the data set or they can be generated independently, if we are looking at contiguity, density, some other indicator that the points belong to the same cluster. And then we need some way of trying to evaluate the clustering. So we're going to also look a bit into that, but this ends up being a major problem in clustering, which is how to validate the clusters that we get. But one important goal that we have to keep in mind is that we want to make data more intelligible. We want to use this to help us understand the data. So there is no fixed recipe that you can apply in all the cases. It depends a lot on what you're trying to work with and how you're trying to understand your data. So let's see an example of a clustering algorithm. This is a simple one that we can use to illustrate the process of grouping points together. So this is k-means clustering. We want to find the best way of grouping our points into k clusters. This parameter, the number of clusters, is previously determined. And we are going to define each cluster by the proximity of the point to the mean of the cluster. So we place each point into the cluster for which the mean point of the cluster is closer to that point. So this, we determine the number of clusters before starting. We have to fix that k value. And this is a partitional clustering. It's all at the same level. It's exclusive. Each point only belongs to one cluster, and it's complete. We don't have points that are left outside unclustered. It's also prototype-based because we are generating these prototypes. The mean point of each cluster will be a prototype, that point, to which we're going to compare the other points to measure the distance, and also that represents each of the clusters. And let's see this Lloyd's algorithm for computing k-means, which basically we start with this k number of centroids, so k number of points that represent the mean of each, the center of each cluster. We start them at random, and then we assign all our data points to their respective clusters by measuring the distance to the different prototypes and assigning to the closest one. Then we're going to update the position of the centroids to the middle point of each cluster, and we repeat this until convergence. So we need some way of starting these iterations, so of randomizing our data. One way is to start with the coordinates of a random set of examples. So we place our centroids at a random set of coordinates taken from our data. This is important because it's useful that our centroids start more or less distributed along with the data and not somewhere very far away from the point. So this would be the 4G method for starting. We start with these points, and then we assign the. No, there are five. There are two almost overlapping here. So these got very close together, but there is a triangle on that side. Okay, so these are two. These are the green triangles and the cyan hexagons. Okay, so we start with the 5 groups here, and then we determine first that we want 5. So this is a choice by the user, and then we assign the clusters, and we start that iteration. Okay? Well, another different way of starting this random start, so placing the centroids first, is to randomly assign each point to one cluster and then measure the midpoint of each cluster. So this random partition method tends to group the centroids together in the center of our distribution because we are computing the mean, and then it starts from there. Regardless of how we start, then the process is the same. We have the data, the initial data. We initialize our centroids. The centroids are independent from the data, so we can move them, and we assign the data points to each cluster depending on the distance to the centroid. So each point will be assigned to the cluster of the closest centroid. And now we update the position of the centroids by computing the mean point of the points in the cluster, and then we recompute the clusters. We reassign the points, we recalculate the mean point, and we do this iteratively until everything converges, or until the change is too small or there is no change in points. So usually this will end up in a configuration where no points change cluster, and so the thing stops. So just going into a bit more detail, you don't need to implement this because you have k-means in scikit-learn, but we can, finding the closest centroids, we simply compute the distances to all the centroids, and then we compute the minimum of all those distances. So we find the index of the centroid that is closer to each point. Then, to move the centroids to the new location, we just for each centroid, we compute the mean point of all the data points that are labeled for that cluster. So we change the position of the centroid by computing the mean points of each cluster. And this is an example of ways to initialize. In Forgy, we need to select a random sample of our data points, but note that we don't want two overlapping points. So we are going to select this random sample without reposition. One way of doing that is shuffling the indices of our points and then taking the first k1 from that. This guarantees that we are selecting a set of points with no repetitions. If we just do a random, say like we did with bootstrapping, just generate a vector with random numbers, they could be repeated, and then we would start with two centroids in the same position. That would not be good. So for random partition, we can just assign data randomly to all the clusters. In this case, each point will be assigned to a cluster, and of course there will be several points to each cluster, so we don't need to worry about repetitions here. And then we compute the centroids by computing the mean points of each cluster, and we start from there. Okay, so now this is a simple algorithm, but it helps us illustrate an important feature here in clustering and in other unsupervised learning problems, which is solved with this expectation maximization algorithm. So we have, in classification, we had one set of features, and we wanted to predict something. So we had the x and the y that we wanted to predict, but we had all that information in our data set. And what we didn't know was the parameters which we would use to instantiate our model, and that would be what we were trying to find with the maximum likelihood, for example. In this case, in clustering, we don't have all the information. So we have a set of features, this x, the set of observed data. We have some parameters that we don't know for our model, for example, the positions of the centroids or something like that. And also, we don't have missing some data that is missing, which is the assignment to the clusters. So we call that Z. This would be something that belongs to our data set. Each point actually belongs to a cluster, but we don't know that information. So this is a latent variable or a hidden variable that we cannot observe. We can try to fit the parameters of our model, for example, the positions of the centroids, by maximizing the likelihood of the parameters given all the data about our data set. That is to say, we're going to maximize the probability of obtaining that set of values assuming our parameters are correct. The problem is that part of this is missing. This is what we do with the while, with what we want to predict in supervised learning, but in this case, part of that information is missing. So this would be the complete data. We would have both the coordinates of the points and the assignment to the clusters, these three clusters. But what we actually have when we're doing clustering is something like this. We only have the coordinates of the points. So we're missing part of the data. Now, the problem is that if we don't have Z, we cannot really compute this immediately, the joint probability distribution of all the data given our parameters, and so we cannot optimize or maximize the likelihood of our parameters to find the parameters. This is why we need two steps here. In order to get an expression for the likelihood that we can maximize, we need to have a guess about that data that is missing, the Z. So this is the expectation step. We assume some set of parameters, the old set of parameters, the initial guess for our parameters, and now we compute the expected values of the hidden variable, that Z, given the values that we have for the X, the observed variable, and the old parameters. So in the case of this clustering example, we would try to estimate the assignment of the points to the clusters, which is the variable we do not observe, from an assumption about our parameters and the known coordinates of the points. So this would give us an expectation, this expectation expression would give us the expression for the likelihood function that then we would try to maximize. So this would be the maximization step. We will obtain a new set of parameters by maximizing the expression we computed previously, where we replace that hidden variable with what would be expected, with the values it would be expected to have, assuming our parameters were correct. And now we are going to repeat this until convergence. So we can illustrate this with k-means. K-means is not really formally an implementation of expectation maximization, because more formally this algorithm deals with probability distribution, and in k-means we are not really doing that. But we'll see this a bit more formally next week with Gaussian mixture models. But for now, this is just the first step for you to get an idea of the algorithm. So we have this distortion measure that is measuring the distance, the square distance between each point and the corresponding centroid for the cases where the point belongs to that cluster. So this is an indication function that is 0 when the point does not belong to that cluster, or 1 if the point belongs to that cluster. So basically we are measuring the square distance from the point to their prototypes, and we're trying to minimize that. We're trying to find the clusters which are more compact around the prototype. So now we can make a guess if we have the positions of these centroids. We can try to make a guess about what would be expected for each point where that point would belong to. And we can do that because we can simply assign them to those that are closest to the point. So this is basically what we do with in the Lloyd's algorithm, which is we assume that the centroids are in that position, so we are going to group all points with the centroid that is closer to each point. And so we are minimizing this. By assigning each point there, we are minimizing this distortion measure. And this now gives us an idea of the function that we can use to place the centroid in the ideal point. Because if each point is assigned to that cluster, now we know that the best way to place the centroid would be at the mean, at the central point of each cluster. So we have now this maximization step in which we maximize that likelihood function. That is, we're going to place the centroid in the center to minimize this distance. So basically, we have this expectation maximization outlined in Lloyd's algorithm. We don't know which cluster each point belongs to, but if we guess the centroid positions, we can see what would be expected of each point if the centroids were there. So we would assign each point to the closest centroid. And now we can optimize the position of the centroids by computing the mean points of each cluster. And we do this repeatedly until we converge. But we'll see this in more detail with Gaussian mixture models next week. So for now, I'm going to give just an example of an application of k-means. K-means is very used for vector quantization. In fact, this was the original application. And the idea here in vector quantization is to compress or simplify the representation of a vector of continuous values into discrete steps. And we're going to show an example of this by quantizing the color values on an image. So I took this example from Wikipedia and chose this example because this image does not have any change in the blue channel. So it only has red and green values here to make these colors. So this means that we can plot the color of each pixel into two axes, red here and green here, and show what are the colors of all the pixels in that image. So this is the distribution of the color values of the image in these two axes, red and green. Now we can use k-means. So we can do that reading the image. We can use this image read function from scikit-image. You have these installed in Anaconda, so you're going to do a similar example in the tutorial. When we do this, we read the image as a NumPy matrix that is three-dimensional. So it has the two dimensionals of the image, the two dimensions of the image, and three layers representing the red, green, and blue channels. But we can, from this array, take only the red and green channels. We can ignore the blue ones. So these are these coordinates here, these values, the two color values for each pixel. And this is just an example how you can do this plot. So you can use the scatter function for plotting. You have one vector for the x-coordinate. This is the first color channel, it's red. The vector for the y-coordinates, so I use the second color channel, green. And then I can give a list of the colors for all the points, as long as this each element of this list is a set of three values for red, green, and blue, and it has the same number of elements as the point I'm plotting. I can specify individual colors for all the plots. So this is just an example of how you can do this, and that S there is the size of the circle which you can control. So the colors are essentially the colors from the original image, and we can do these plots in this way. But now we have here it is. A ordem? Sim. Yeah, because if you mix red and green, you get yellow. So if everything is at 0, you have black. And these are these colors here. So some points here have the maximum red and green. So these would be around here. There are very dark spots here, and these have very close to 0, and so these are these pixels here.
All colors on the image?
Yes, so this is the set of all pixels on the image represented on the red and green axis. So this image array, now we have all the two-dimensional coordinates of the pixels in color space, and we can compute with k-means, apply k-means, and compute 64 centroids. So in this case, we specify k to be 64, and we obtain these centroids. So what I'm doing here, I just imported k-means from scikit-learn. So I create the object. This works similar to what you already did. We have this fit method, and we train the k-means clustering, so it computes the position of all these centroids. Then we get this, from this attribute here, we get the centers of the clusters, and we can represent all of them with these crosses here. Yeah? Here, I specified that there are 64 clusters. So when I compute k-means, k64, it will give me 64 centroids. Okay? So now I have 64 centroids distributed in the same shape, let's say, as the original colors are distributed. And now I can just, on the color array, I can change the red and green values to be equal to the centroid. So these points all have different colors, but I can make them the same as the centroid and simplify the image now. So this image is the original one. This only has 64 colors, and we can barely see any difference here. So we can go a bit more. I can use k equals to 8 and compress this to 8 colors. So basically, we'll have 3 bits here. And now I can change the color of each point. So I don't know if you can see the difference here. So all these points now have the color of the centroid. They had originally these colors here, the values here of red and green, but now I change their color to match the centroid. And I do this for each point, and now I have the image. This is a more compressed image in only 8 colors. So this is one example of what we can do with k-means. We can use that the property that we are able to specify the number of centroids, and the centroids get distributed in the same way as the original data. So then we can convert the data into just the centroids and simplify the data that we have. So to sum up this part, we saw a basic introduction to the idea of clustering, grouping things by how similar they are. We saw different kinds of clustering: partitional, hierarchical, complete. The way points belong to the cluster can also vary, so we can have fuzzy or probabilistic clustering along with free clustering. And we have different types of clustering. We saw this prototype-based clustering now in k-means. We're going to see the others in the next sessions. And we saw the basic notion of this idea of the expectation maximization algorithm. This is an important notion because when we are dealing in this case with unsupervised learning, we are only looking at parts of the data. So we can imagine that part of what we're trying to use, part of the information that we're trying to use is actually hidden. And so in order to optimize the parameters of any model that we use, we need to make a guess about what is hidden. And this would be the expectation part, and then we use that to review, to update our parameters. However, in order to make that guess, we also need an initial guess of the parameters, and so we need this back and forth between the two until things converge. So we have these sections of Alpide and Bishop and Markman, if you want to look into. Markman also has an interesting relation between k-means and self-organizing maps that we saw in last time. So they're actually similar in the sense that we are moving those centroids around the data space. The big difference is that in the self-organizing map we also have this topology of the network that we are projecting into the data space.